Hello, everyone. So today we are going to continue with our discussion on surface Plasmon Polariton. So we have solved the Maxwell's equation. We had got our relations for the TM and TE mode. If you recall that we get the SPP only for the TM modes. For the TE mode, there is no solution for the surface Plasmon Polariton. So for TM mode, practically we have the HY component and the EX and EZ components. Okay, so transverse magnetic. So there is no Z component for H. Now the boundary condition is that our boundary is at Z equal to 0, that is the interface between the conductor and the dielectric. So at that point, at Z equal to 0, the in plane component HY is continuous. This is coming from the fact that KF, there is no free current at the interface phase. So if you use this relation to the equations we had arrived at from the TM modes, you'll get to basically A1 is equal to A2, or rather in our notation we have conductor and the dielectric. Okay, so this is also conductor and the dielectric. And for this, from the electric field, the parallel component of electric field is also continuous, and that gives you a relation, typically your Kd by epsilon d is equal to Kc by epsilon c. So it's the conductor and the dielectric, the ratio of the wave vector to the epsilon is, there's a negative sign, sorry. So this is what it is. Now with all these relations, so we have this, and actually this we have AC is equal to AD, this has been used, and that brings us to the second relation, this which I call equation 1. Now if you recall, we also had two more equations from the wave relations that we had. So we had Kd, which is the dielectric, Kd square plus K0 square epsilon d minus Kx square was 0, and similarly Kc square plus K0 square epsilon c minus Kx square was 0. So we had these relations earlier, and these we call as set 2, and with these using 1 and 2, if you eliminate all your Kd and Kc from these two relations, these three we can eliminate Kd and Kc. I'm not doing the maths here. What you arrive at is Kx is equal to K0 square root so this is the relation between the propagation vector Kx and the frequency. Yeah, K0 will have your omega, and so this will eventually lead to the dispersion relation. This comes from the fact that your epsilon will be a function of omega, and dispersion relation is a relation between your Kx and omega. So this brings you to your dispersion relation, which is quite an elaborate way to solve. So what we can do is we can put in some forms for epsilon. If you remember, the epsilon c, which is the dielectric constant of the conductor, which is a metal, can be written as omega p square 1 minus omega p square by omega square. Of course, here what we are doing is neglecting gamma. What was gamma? Gamma was the imaginary part, right? So it was included when we consider all the loss mechanisms in the system. So here we are neglecting gamma, so all the damping constants and all, it's a very weak scattering and damping, so we consider epsilon to be real. Okay, so if this is the case, then one can show, if you plug it in, and epsilon d, the dielectric constant of the dielectric is considered to be, let's say for silicon or for air, you can consider it to be 1. And then what you get is, if you plot the dispersion curve, so let's say we plot kx versus omega. If you recall, for the volume plasmons, our dispersion curve went like this, where at kx equal to 0, it was omega p, the volume plasmon resonance, and our light line went something like this. So this is a little different. So this line would practically tend towards the light line at infinity. So that was what we had done so far, that at omega p it came and met. And now what we are plotting is the line corresponding to the surface plasmon polariton. I'll show you why this happens here, but typically this one comes to be like the of this form, where asymptotically it tries to reach omega sp. So at kx tending to infinity, the omega is omega sp. So this is how the dispersion relation looks like. Let's do a little more maths here. So of course we get to this. How do we get to this omega sp, and what is omega sp? This is what we want to find out. So if you see that we have already got our relation from here, this relation. So kx is k naught epsilon c epsilon d by epsilon c plus epsilon d. So if this is the relation, and I said we will put in epsilon d is just the dielectric constant for the dielectric, and in case of epsilon c we will replace it by 1 minus omega p square by omega square. If you plug these values in, you what we get is kx is k naught something like this, epsilon d omega square minus, please do the maths yourself once. This is what you get when you plug in all the epsilons in this. And now for kx tending to infinity, basically the denominator tends to 0, right? So we have epsilon d omega square plus omega square minus omega p square tends to 0. So this is the value of omega at kx equal to infinity, and if you find out what it is, so omega, now we call this frequency omega sp, that is the frequency at very large values of kx. Omega sp is nothing but omega p by square root of 1 plus epsilon d square. Okay, so this is what we call the surface plasmon polariton, the surface plasmon frequency. Fine, omega sp. Now in all this treatment what we had, so if we look into it at this particular frequency, so kx tending to infinity, what does that mean? So kx is nothing but, as we know, is omega by v. So when kx tends to infinity, v tends to 0. That is, the case becomes quite like aqueous electrostatic character So it's not really a propagating thing, because your velocity tends to 0, and at this point it is known as the surface plasmons. So surface plasmons occur when omega is equal to omega sp. That is, at this particular resonant frequency, your kx tends to infinity, your velocity tends to 0. Now, but in all this, what we had considered is that the gamma, that is the damping coefficient, was negligible, right? This is what we had considered. Now, for real metals, we do still have a finite gamma. Gamma is non-zero. So if gamma is non-zero, of course, that brings you that there is a I gamma in your gamma omega in your expression for epsilon here. So this then becomes some omega p square by omega square minus I omega gamma. So if that is the case, your epsilon becomes imaginary, and then you get an imaginary part in your kx as well. So what does that imply? That first and foremost, so your kx cannot be infinity. There is some sort of attenuation because of this finite gamma. So this finite gamma will give you some attenuation of the field. I told you that this imaginary part leads to a decrease in the amplitude, and so one can even define something like a propagation length beyond which the intensity dies as 1 by E intensity. So L is given by 1 by 2 imaginary kx. Now this imaginary kx will go to 0 if gamma is 0, but in real cases gamma is non-zero, and so there will be an imaginary part to your kx, and that will lead to some sort of attenuation of these surface plasmon fields. Okay, so this would be the propagation length. Now the second situation is when kx is very small, when kx is small. So this is the point where we are reaching this other end of this. So we are considering this region. Okay, as we see that this is the point where the line merges with the light line. Let's see whether we get this from the expression we have. So what we have is kx is k naught epsilon d epsilon c by epsilon c plus epsilon d, right? This is what we had. Now what we put is epsilon c was 1 minus omega p square by omega square. Knowing that omega is small in this case, what one can write is this is nearly equal to minus omega p square, ignoring the 1, because the second term will be very large, omega being small, much smaller than omega p. So what happens here is, if we do this approximation and plug it in here and consider that omega square term will be very small in this expression, what you will get is this becomes nearly equal to, please do the maths, I'm not doing it, it comes to this. Okay, or practically your kx square is now nearly equal to k0 square epsilon d. This is nothing but this is the light line, this is the light line for the dielectric with dielectric constant epsilon d. Okay, that's why we see at low omegas this merges with the light line. So that is where we stop today. So this is where the dispersion of these materials come. Thank you.